Space groups is usually how crystallographers, chemists, and physicists all talk to one another. The symmetry operations get very complex. So the old timers who had to really know these things ended up, would probably know every single symmetry operation that happens within a crystal. They had to do the mathematics associated with it. In fact, a lot of it happened in Buffalo, New York when it came to crystals. There is, what was it, the Woodward Institute. Have you guys ever heard of that? Let me try and find it. Yep, the Hauptmann Woodward Institute. It was one of the biggest centers of crystallographic discoveries, and it's named after the people, one who did a lot of the mathematics. One of the guys was actually a mathematician. All he did was the math to solve crystal structures. If you do get a chance, if you're interested in this sort of stuff, I highly suggest to apply for an REU there, because it is like a top-notch area that all crystallographers know. Okay. Generally, most scientists and material scientists are aware of this place too, just because of how important crystal structures are to those sciences. Okay, so I'm sure those guys know all the space groups and know what their exact symmetry operations look like. I'm not going to make you memorize all those different point groups. One, because that's hellish. Two, there are books to look at it. And three, even understanding what symmetry operations are happening in there are confusing. Today, it's mainly done by computers because it can do a bunch of matrix operations incredibly fast and give you the clear indication of what it is. But I do want you to know what those symmetry operations mean. Those are important. So let's talk about the 230 space groups. Okay. So you may have learned about point groups. And the symmetry of molecules. In a point group, what doesn't change? I think I said it a little bit ago. There's one specific point that doesn't change in a point group. Space groups. What don't you think changes in a space group? The spacing. Okay. I guess I am using those synonymously. What do you imagine as space versus spacing? The space is in the whole area of the unit cell is what I'm talking about, not the spacing between specific atoms. So yes, good clarification point. So what do crystals have, or unit cells have, that molecules don't have? What type of symmetry? Mm-hmm. Yeah, periodic or translational symmetry. So crystals have an additional layer that they can have that molecules just don't have. So due to the translational symmetry, of a unit cell. The space is conserved. And that's where we get a space group from. At this juncture, we are finally considering atoms. Okay. What I do want you to be able to do is to look at a point group, understand what its Bravais lattice is, and to understand the symmetry operations that are happening. So let's talk about the nomenclature and the symbols. Philip Coppens taught me crystallography at the University of Buffalo. It was the hardest class I ever took in my life. We got the highest grades he ever gave out. Me and one other guy, Mike Gross, who works for the, I think, California EPA right now, we got a B+. There were professional crystallographers in the class that failed the class, which was intense. He was Dutch, and I remember one of my colleagues was teaching PChem for him, and he said, like, you know, this is a really hard question. Are we sure we want to do it? And I remember him saying, yeah, yes, we want to weed out the weak ones. So he loved me because I was a theoretician, and I believe for no other reason. Avid cross-country skier, and I think he actually died in the parking lot at UB. He was in his 80s when he passed away. So, but I remember him saying, it is an easy way to determine the crystal symmetry. He was Dutch, and since I'm going to the Netherlands, I feel like I'll feel the spirit of Dr. Coppens as I'm traveling. I don't know. What was that? The food in the Netherlands? No, Finland was horrible. We'll see about the Netherlands. They have to have something good. They have chocolate. It's got to be good. I don't know. Burger King, they don't have saunas there. There is a sauna if you go to the Burger Kings in Finland. They usually have saunas. A Whopper in the sauna is crazy. Yep. This is all we talked about after like 3 weeks ago. Yep. I didn't even get to go in it though, but I did get to jump into the Baltic Ocean. So that cool. She's Canadian. Don't let her kid you. So, I remember Dr. Coppens going up and saying, oh, it is very simple and easy to understand these. Let's pick one. Just 118? I'm glad you gave me the number. It's very trivial to understand where all those positions are and what's going on, right? Okay. Even I myself, as I would say a solid state theoretician, I look at these, I have ideas of what symmetry operations are happening here. But if I were to look at a crystal with this specific space group, I wouldn't be able to tell you it without a solver or a computer to do this for me because there's just too much going on. However, Dr. Coppens would be able to look at that and immediately identify them. But he was also somebody who developed this from the ground up. So in the 70s, if you solved the crystal structure, you were given a PhD. Nowadays, it can be done on a benchtop within an hour. That would not get you a PhD. But looking at this, what I want you to eventually be able to do is to look at this and understand what symmetry operations are happening here, where we have things called glide planes, mirror planes, rotational axes along here. This is a C2. You'll be able to look at this and have an idea of what these symmetry operations mean. Okay? I don't expect you to be able to pick up a crystal structure and go, yep, that's 114 right there. Knew it. Do they ever find two space groups? Mathematically, it is supposedly impossible to get beyond these 230. They do find quasi-crystals, so there were certain crystals that were suggested to not exist due to them not being periodic and having a C5 symmetry axis, but that was found to not be true. So I will say at this time, we believe there are 230, and there are mathematical proofs to show that there are 230. I will not say that we are not going to go beyond that, because I don't know. But the idea of it being easy is not easy, and those who say it's easy exist on a different mental plane than me. Generally, though, to do the nomenclature, we start with the Bravais lattice. And then it's followed by up to 4 different symmetry operations. And this is according to the crystal viewing direction we just talked about. So as Katie identified, they are given numbers, and that is helpful when you're looking them up in tables. But they also have this notation. I'm going to use a couple different colors. Let's do green, red. This will look ugly, but we'll try it. C, A, 2/1. Okay, and these are subscripts. The P, what do you think the P stands for? Yep, it's a primitive cell. That's a subscript of a subscript. So the way that this crystal system is, this is aligned with the different axes. It's telling you what it's parallel to. So what is this C parallel to? Which axis? Or excuse me, perpendicular to? A, B, C. It's telling you what axes they're trying to go along. So this is an, what is it? A C glide plane perpendicular to A, axis A. What's this orange symbol telling us then? That was a seed glide perpendicular to A. What's this one? Yeah. Yep. And now for the blue. This is known as a screw axis. There is no analog to a molecule with this, other than maybe like DNA. A 2-1 screw axis parallel to C.
How do you know that it's parallel to C? Just because that's the first one in the grouping, or is it?
That it's parallel or it's C? Or what do you?
That's C.
So at least with this unit cell, since it's aligned A, B, C, we know. Okay. But notice there are up to four other symmetry operations. It doesn't always mean this goes A, B, and C. It could be down different viewing planes.
And it just depends on what type of cell it is?
Yes. It depends on what the Bravais lattice is and what type of crystal system it is. And they're all different.
Easy, right?
No, there are standards based upon the crystal viewing direction. So it is standardized. It's just you have to memorize a lot of that, and honestly, it is not worth your time, I believe. You have systems that solve it for you automatically, and honestly, matrix representations of these symmetry elements are way easier for me to get, and they're more mathematical, less visual. I like math over looking at stuff and saying, I feel like this looks like a 2-1 screw axis. I'm not good at that.
You just have a huge matrix for it?
We will talk about those matrix elements next. Are there any questions right now? If I were to give you something like this, what I would want you to know is that there's a C glide, an A glide, and a 2-1 screw axis, and I would want you to understand what symmetry operations those are. We're going to talk about all of these ones and other symmetry elements, but by the end for the exam, I would like you to know what these symmetry elements mean. Not right now, but by the exam. Okay. The upcoming exam.